All right, it's time for another math video. So today, we're going to be taking a look at the opposite angles of an inscribed quadrilateral. So what does that mean? Well, inscribed means it's inside the circle, right? The quadrilateral part comes from this being a four-sided figure that is inside the circle. And when I say opposite angles, what I mean is, I want you to think about like SOHCAHTOA, right? Opposite means across from. So if angle A is the angle we're looking at in this diagram, then angle C would be its opposite partner. So A and C are going to be supplementary according to this theorem, meaning they add to 180. Same thing with B and D in this diagram. They will also add to 180, therefore be supplementary. So again, the theorem says the opposite angles, the ones across from each other, are of an inscribed quadrilateral, sorry, having trouble reading, are going to be supplementary. So why is this true? Let's prove it. All right, so first things first, we need our circle. Got it. All right, now we need to make an inscribed quadrilateral. So I'm going to do that by placing 4 points fairly randomly along the circle's circumference. All right, now I'm going to connect those and create that quadrilateral. We'll later label these A, B, C, and D appropriately. And we'll get down to business to prove that the opposite angles in this diagram are supplementary. And remember, these points that I'm putting down are mostly random. They do not matter where they are as long as they're along the circumference. I can move them around however I want, make any diagram as long as it's an inscribed quadrilateral, and this following statement will be true. So let's label this. How about A, B, C, D? And let's get some colors in here. So let's talk about angle A being red and angle C, its partner, its opposite partner. Let's have it be pink. Let's use a different color pink. Here's my more vibrant color pink. There we go, that's vibrant. All right, and we've got angle B and its opposite, angle D. So again, what we're trying to prove is that the opposite angles of this inscribed quadrilateral, angles A and C, and as well as angles B and D, are both pairs are going to be supplementary. So let's write that. We are trying to prove that angle A, which I will do in red, angle A and angle C in this case, because that's its opposite right here, not A and B, but A and C in this diagram, are supplementary. And, I suppose, ampersand, and that was a terrible one. I'm going to need another one too down here. That was a much better one. Angle B and angle D are going to be supplementary. Oh. All right, so now that we have that written, we know what our goal is. It's time to get down to it. So the first thing I'm going to do is I'm going to draw your attention to these angles right here. So let's look at angle A. Angle A is an inscribed angle. We talked about this last time. Remember, inscribed angles are angles that have their vertex on the circumference and two other points on the circumference. So they open up into an arc on the circle. And so this angle A is opening up into arc DCB. And there's a connection there. Whatever the measure of DCB is, angle A is going to be half that, or another way to say it would be that whatever angle A is, let's say angle A is 30, then the arc DCB, the arc it opens up into, will be double that. So if this is 30, then this would be 60, and a rather large 60 based on my diagram. All right, so let's use this knowledge and let's write it down. We know it, let's write it. So we're going to say that arc DCB, let me highlight that in red. This arc right here that angle A opens up into, arc DCB, the measure of it, is going to be equal to double the measure of angle A. And we know that because angle A is an inscribed angle. So I'm going to write that. By inscribed angles. We squeezed it in there. All right, so by inscribed angles. And you'll notice that its opposite angle, angle C, is also an inscribed angle. And it opens up into this arc, arc DAB on them haters. All right, so we've got arc DAB. And we know that's going to be double the measure of angle C. Again, by inscribed angles, right? Same dumb crap. All right, so we've written this, and if you notice, and I hope you have, that these two arcs, DCB and DAB, if you follow them on the circle up here, put together, if we sum them together, are going to create a full circle arc, right? A full arc around the circle, and we know those arcs are 360, right? The circle is 360 no scope, right? So we're going to write that the sum of these two arcs is going to equal 360. So we have the measure of DBC plus the measure of DAB, and that's going to equal 360 by definition of full circle arc. All right, let's fill in the things. So we know this arc, DCB, plus arc DAB. When their measures are added together, they're going to add up to 360 because altogether they make a full circle arc. Oh, whoa, can't see me. All right, so altogether they make a full circle arc. Let's try to zoom out a little bit. There we go. You see all my pens over here. All right, so these two arcs put together are going to add to 360 because that is what a full circle arc is. It's a full circle, and full circles are 360 degrees. All right, so maybe you're seeing where we're going with this, right? We know DCB is the same thing as 2 times the measure of angle A. So I'm going to switch those out here and here. Same thing with DAB being 2 times the measure of angle C. I'm going to switch out DAB with 2 times the measure of angle C, and we're going to know that these two are going to add up to 360. So let me write that. So by substitution, we know that 2 times the measure of angle A plus 2 times the measure of angle C is going to equal 360. So again, I'm just taking this equation right here, and I'm switching it out with, instead of writing DCB, I'm going to write 2 times the measure of angle A, because they are one and the same. And instead of writing DAB, I'm going to write 2 times the measure of angle C, because they are one and the same. And now I have a new equation that says 2 times the measure of angle A plus 2 times the measure of angle C is going to get us 360. So our next step is to do algebra. Therefore, when we divide everything by 2, the measure of angle A plus the measure of angle C is going to equal, well, 360 divided by 2, which of course is 180, and you can tell we're almost there. So the measure of angle A plus the measure of angle C is going to equal 180, and therefore, by definition, angle A, ampersand, are supplementary, and that's what we wanted, right? All right, so how do we get the last little bit of this? We proved A and C are supplementary. How do we know B and D are supplementary as well? We could do the same process. We could write, by similar logic, angle B and angle D are going to be supplementary. However, there is something else we can do. So notice that A and C and D and B are part of a quadrilateral, right? And we know quads always add up to 360. So if I know A and C are 180, then if I subtract those, what's left over will be what D and B add up to. Well, if they're 180 and I subtract them from the whole thing, which is 360, then what I'm left over with is 180 for these, which by definition means they are supplementary. So what I'm going to write is down here, in addition to all this, therefore, by interior angles, sum, let's do that, sum, S-U-M, not S-O-M-E, the sum of interior angles of a quadrilateral, angle B, which I did in dark green, ampersand, angle D, which I did in light green, are supplementary. And that's the end of the proof. I have proven that angle A and C are supplementary. I've proven that therefore angle B and D are supplementary. And now I have shown that the quadrilateral ABCD that is inscribed in the circle has to have opposite angles supplementary. All right, so this is also true. Get this out of here. I guess the statement's converse is true, this theorem, that if the angles in a quadrilateral are not supplementary, then they cannot be inscribed in a circle. So what do I mean by that? So here's a quadrilateral, right? They don't always exist in circles. call it A, B, C, D. All right, so if I told you that angle A was, I don't know, how about 100 degrees, right? And I told you that angle C was 200 degrees. This is fine, right? Altogether, they have to add the 360. That's really the only rules here. So if this is 300, I've got 60 to split between the two. Let's make it 20 degrees, and I suppose maybe 40 degrees. Sticking with the Christmas colors here. All right, so altogether this is 360 because that's 300 and that's 60 and that makes 360. So it checks out, right? This is a quadrilateral. It's got 4 sides and 4 angles that sum to 360, right? So it's all good. But you might notice that these opposite angles, here and here and here and here, are not supplementary. And so if they aren't supplementary, that means there's no way to connect all these dots by drawing a circle. There's no way to inscribe this quadrilateral, so I guess we would call this not inscribable. Right? In means not, or I'm sorry, in means not. In means inside, not means can't be inside. So you can't put this inside a circle, right? Some might think we could simplify this to describable, right? D means not. That's where I was going with that joke earlier, and I just killed it. But of course, describable is another word entirely and isn't funny and shouldn't be included in the YouTube video. All right, so cannot put this inside a circle. If the angles, opposite angles were supplementary, then you would know you could put it inside a circle. All right, so lastly, let's flip this paper around and do something with it. I hope that doesn't annoy you that I'm reusing the paper. Maybe it fills you with joy. Let's cover that up. That way you can't even tell. Through the magic of YouTube, I'll edit this out totally. All right, so what if we're given a quadrilateral and it's inscribed in a circle that I did not draw? Let's do some damage control. Oh, that's good. Oh, that's very good. All right, yeah. That's amazing. All right, good recovery. Stuck the landing. All right, so ABCD is inside the circle here. So it is an inscribed quadrilateral. And if we are given that maybe angle C right here is 45 degrees. Let's say it's 45. And we know that angle D is perhaps 35 degrees. We'll stick with the 5s here. We can figure out the angles of the rest of the quadrilateral as well as these different arc lengths here. So this is kind of neat. So if angle C is 45, well, because this is an inscribed quad, I know that this opposite angle over here, angle A, will be supplementary with it. So if this is 45, this is going to be 135 because those sum to 180. And in similar fashion, I know if angle D is 35, then its opposite angle on this diagram, angle B, will also be supplementary. So it's going to be, what are we talking here, 145? Yes, I believe that is correct. 145, 14 and 30 makes 175 and 5 makes 10. Yes, okay, good. Just had a mental math breakdown there. All right, so opposite angles are supplementary. This is an inscribed quad. Everything looks good. You might notice that angle D is an inscribed, which means this arc right here is 35, or I'm sorry, double 35 degrees, which is 70. Their mental math breakdown. And this is 145, so doubling that is going to be the remainder, but it might be easier to think about it this way. These two arcs together make 360, so if I subtract 70, I get the arc that remains, and that is going to be 290. Which of course is double of this angle right here, this inscribed angle, angle B. We also know that angle A is 135, so between here and here, the arc that it opens up into will be double that. So we get 200 when we double 100 and 70 when we double 35. So we're talking 270 degrees. And this 45 degree angle opens up into this seemingly not 90 degree arc, but we know that it is because it's double whatever this angle is. All right, so we know all these different arcs and what their lengths are, and we're able to figure out the different inscribed angles from inside. There's ways to do different math here to figure out the individual little parts like arc AB. It's a little more complicated than this video wants to get into right now, but that's the idea. So just by knowing that we have a quadrilateral inside a circle, an inscribed quadrilateral, we can figure out a lot of things about its angles, and this is going to be really useful for doing some mathematical things with circles later on. All right, so that's inscribed angles of a quadrilateral. I believe this is 15-2 in your book. Not that that matters. And I will see you next time for 15-3 and a lot more proofs.